Hello, my name is Rune Ondro and this is my second video about fluid dynamics and more specifically about Bernoulli's principle and how the scientific community fails to explain many aspects of this in a correct manner to the wider public, and even fails to agree on explanations to the simplest applications of Bernoulli's principle. By the scientific community, I mean everything from high-end university to popular science publications. My last video was about how Albert Einstein and others absolutely bungled the understanding of lift of an airfoil. In this video, I will address more mundane examples that are often used in a classroom setting to supposedly demonstrate the effect of Bernoulli's principle. I will use some clips from lectures and educational videos that I have found on the internet. Very unfortunate for the professors that I have chosen to expose for their ignorance, because there are very many to choose from. There are those professors that explain Bernoulli's principle in an absolutely correct manner, but for some reason it is not easy to find anyone who tries to challenge the wrong explanations of other professors. I am not a professor though, so I can say whatever I like. My main candidate in this video for demonstrating the misconceptions of Bernoulli's principle is the unfortunate Dr. Boyd F. Edwards of Utah State University. In this video, to which I will give the link in the description, he gets pretty much everything wrong. But it starts off well enough by showing the corresponding pressure to a fluid flowing through a venturi, and the explanation here is completely fine.
This is a venturi tube. I've got a source of air that'll come in to this side of the tube. It'll pass through this region where the tube is wide, and then here where the tube is quite narrow, and then back to wide again. And because this spot has a smaller cross-sectional area, the air has to flow faster here. So we've got a high velocity region here, a low velocity region here. But Bernoulli's principle says that the higher the velocity, the lower the pressure. What you'll see is when we turn on the air, this column of water in the middle will rise, because the pressure here is lower and essentially acts as a suction for the water. So this one will rise higher than either the other two. All right, another example. The tank is open to the atmosphere at the top. Find an expression for the speed of the liquid leaving the pipe at the bottom.
He also says something else that is absolutely correct. This is his very last example in his video and shows water running out of a container. This is pretty much the simplest use of Bernoulli's principle that one can find.
Atmospheric pressure on the top, but we're also allowing this to exit the liquid at the bottom. So there's going to be atmospheric pressure at the bottom. Now you say, well, hang on, what does it happen? Doesn't the pressure increase with depth? And it does. So there'll be increasing pressure as we get deeper and deeper, and then as we go between here and here, the pressure is going to be atmospheric again.
I will not bore you with his calculations. The answer to the velocity of the water is as shown here, but the most important thing is what he says next.
Because it's open to the atmosphere, and anything that's open to the atmosphere is at atmospheric pressure.
It amazes me how people can have two contradicting notions in their head at one time and seemingly not have any issue with it. Because in other examples in this video, he says something totally different. For example, as shown here.
This is another demonstration of Bernoulli's principle. I'm going to create a stream of air using this hose, and send it across this piece of paper that's been taped to the tabletop and is dangling off of the edge of the tabletop. What you'll be looking for is what you'll be thinking about, hopefully, is that the velocity will be high on the top side of this paper. That high velocity means the pressure will be low because it's open to the atmosphere. And anything that's open to the atmosphere is at atmospheric pressure.
Well, he just said that anything that is open to the atmosphere is at atmospheric pressure. How come he just changed his mind and now says that the air from the tube entering the atmosphere has a lower pressure?
And the pressure on the bottom side of the paper is atmospheric pressure, and so it will be greater than that low pressure on top, and the atmospheric pressure will push the piece of paper up and overcome the small amount of weight that this paper has and bring it into a vertical position just below the stream of air. Yeah, so we've now got the paper up, we've got high velocity and low pressure here.
Well, this is completely wrong. This has very little to do with the Bernoulli principle and very much to do with the Coanda effect. This effect is the tendency a stream of fluid has to attach itself to a surface. The air has forward momentum and it takes a force to change its direction down along the paper. And due to Newton's third law, the paper will feel the opposite force and raise to a near horizontal position. Professor Edwards is not the only one who gets this wrong. For example, here is Professor Roger Moore at University of Alberta.
So we've just seen the Bernoulli effect demonstrated with a narrowing tube, but there's another way you can demonstrate it that's quite easy to do at home, but is also very, very relevant to modern travel arrangements. So here we have a piece of paper, and all I'm going to do is just blow down on the top of the piece of paper and watch what happens. And what you can see is, although I'm blowing down on the top of the paper is lifting, and that's due to the fact that the air moving over the top surface of the paper has a lower pressure than the air that's stationary underneath the pressure, and it causes it to lift. This is exactly the same way that an aircraft wing generates lift. The shape of the wing forces the air that travels over the top surface to move at a higher velocity than the air that travels underneath, with the result that you get a lower pressure on top of the wing that causes lift and causes the aircraft to rise from the ground, which is what enables all modern jet flights.
And here we go. How can one possibly prove that one does not understand Bernoulli's principle without mentioning the lift of an airfoil? This is what NASA has to say about that. And of course, Professor Edwards will not do any worse.
This is the way airfoils work. What happens in an airfoil is that two air molecules, one that ends up going above the wing and the other one that goes below the wing, the one that ends up going over the wing travels a farther distance than the one that's below the wing. And if they meet up after they both made their trek across the airfoil, if they meet up at the same time, so they started out together and they end up together, that would be a streamlined flow, a steady flow. Then that would mean, in order for them to meet up after their journey is over, that would mean that the guy on the top had to be traveling faster. If he's traveling faster, that's a high velocity, and the pressure must therefore be lower by Bernoulli's principle. And down here, we have a low velocity and a high pressure. So what that says is the there's a higher pressure pushing up on the wing than there is pushing down on the wing. This is a low pressure pushing down and a high pressure pushing up. Which one wins? Well, the one that's pushing up. That's what provides the lift for the wing. That's only usually 30 or 40% of the lift provided for wings. The other way that you can provide lift is by putting these ailerons down or actually just tilting the wing up so that the air hits it and reflects downward. That's called dynamic pressure. But this Bernoulli principle is an important piece of the puzzle.
I addressed this theory in my last video. Albert Einstein claimed that it was possible to fly at level flight without using any energy, provided that the wings had a profile that could make use of this so-called Bernoulli lift. This means that a wing could fly through the air without changing the state of the air and therefore not lose any energy. One of the examples I used to disprove this was to imagine that one puts a radio-controlled helicopter inside a box that again is sitting on a scale. The rotor of this helicopter is fitting with these magical airfoils that supposedly make it possible to fly using this Bernoulli lift. If the box is empty, the scale will only measure the weight of the box. If the helicopter is at rest at the bottom of the box, the scale will measure the combined weight of the box and the helicopter. But if the helicopter is flying without disturbing the air inside the box, how can the scale detect if the helicopter is there or not? Gravity is pulling on all objects, and the mass of the helicopter can't just simply vanish. The only way this can make sense is if the airfoils of the helicopter push air down towards the bottom of the box so that the scale can detect the added pressure. This explanation is also otherwise called the Newton lift of an airfoil. Professor Edwards suggests that one can explain 30 to 40% of the lift of an airfoil by using this Bernoulli lift theory. So then, that would leave only 60 to 70% of the weight to be picked up by the scale. But one can't get 30–40% of the mass of any object to vanish more than one can get 100% of the mass to vanish. It is equally impossible and equally wrong.
All right, conceptual example. When a truck is stationary, the tarp on the truck is flat. So if it's just sitting here, but it bulges upward and the truck moves down the highway.
Conceptual example. Right. Well, he has not demonstrated to have much concept about Bernoulli's principles so far, and he will not do any better here. I have to say that I've actually never seen this example presented by a university professor before, but this was the very first example presented to me when my father wanted to introduce me to the concept of Bernoulli's principle. I really could not make any sense of his explanation then, and it does not make any more sense now.
Well, as it's moving down the highway, the truck's velocity is this way. It's moving through the fluid, but from the truck's perspective, the air is rushing over the top of the truck, as well as below the truck and along the sides of the truck at a high velocity. So above the tarp, the velocity is high, and the pressure must therefore be low.
Okay, so let's entertain this idea a little. Here we have a spinning disk of solid material. Above it we have a barometer. If Professor Edwards is correct, when the disk is spinning, one should then expect that the barometer would record a lower pressure. Here we have Bernoulli's equation, which describes the relation between pressure and velocity of a fluid along a streamline. Now, where are the elements in this equation that describe the pressure within the fluid and the velocity of a solid surface under it?
Below the tarp, whatever's between the, well, you got air between the tarp and whatever the contents are in the trailer. The air is not moving at all, or at least not as much as it is on top of the tarp. You'll have a low velocity and a high pressure. So you get high pressure below and a low pressure above because it's high velocity.
Let's see what happens to the air under the canvas. Before the truck starts moving, the air under the canvas is at rest. When the truck accelerates, the engine of the truck will do work on the air inside the truck, giving it a certain kinetic energy in the forward direction. So then, the left-hand side of this equation will be greater than the right-hand side, and Bernoulli's equation does not longer apply. But nothing else has been done that would indicate that the pressure inside the truck would increase. So, what Edwards did was to use Bernoulli's equation to compare two different volumes of air, of which one volume has had mechanical work done to it. This is not how Bernoulli's equation should be applied. Here, Professor Edwards is describing how the air is flowing over the truck.
So high V and a low P on top. And here we have a low V and a high P. So the pressure is higher underneath, that causes the tarp to come up.
No, the air is pulling on the tarp like the air is pulling on a sail. This video shows how the direction of an airflow will change when it flows around an object. Let's consider a tube looking like this. When we measure the pressure at the different portions of the tube, we will see that the wider part has a higher pressure than the thinner part. And when we change the position of the manometer to measure the pressure at the inner side of the bend, we will see that we will get an even lower pressure. The very same thing will be the case where the airflow is turning over the canvas covering the truck. But the most common fallacy is that one simply fails to recognize this.
Because it's open to the atmosphere. And anything that's open to the atmosphere is at atmospheric pressure.
Okay, so now we are going to learn how to use this Bernoulli.
So here we have Professor Ramamurthy Shankar at Yale University to demonstrate that he does not understand Bernoulli's principle by wrongly explaining the forces that works on a curveball.
I'll give you some quantitative examples. So one example is a baseball. Here's a baseball coursing through air. If you like, you can sit and ride with the baseball and say the air is going backwards. And the baseball is going that way. Now suppose you spin the baseball like this. If you spin the baseball, it carries some of its own air due to friction between the leather and the air. So that velocity is counter to the velocity of the drift you have on the top and additive in the bottom. So the actual air velocity in the bottom will be more in the bottom and less in the top because you're subtracting this vector from the top and adding this vector in the bottom. So if the velocity is different, this is the higher velocity region, this is the lower velocity region. So pressure here will be less than the pressure there, so the ball will sink down.
I would say that the main thing that Professor Shankar has misunderstood here is that the Bernoulli's principle does not longer apply if mechanical work is being done on a fluid. It is only if the fluid does work on itself. In this case, it is the ball itself that carries fluid along with it, and in any case, why should that matter? This is wrong at so many levels. First, the same principle applies here as is the case with the tarp covering the moving truck. One can't use Bernoulli's principle to compare pressure changes in a fluid near a moving solid surface. There is nothing in Bernoulli's equation that would describe this. Secondly, the rotating ball is transferring energy to the boundary layer of air around it. Then one is comparing air in its original state to air that has been added energy to. Again, where are the elements in Bernoulli's equation that would describe this? I will let Diane Coven, or Physics Girl as she calls herself, give a more correct explanation.
How did you do that?
Well, it's a pretty standard technique in soccer to use the inside of your foot to generate spin on the ball. That spin is actually going to make the ball curve into the goal.
Let's take a look at how that happens. As Kyle kicks the ball with his right foot on the right side, he imparts a spin on the ball. The ball traveling in this direction means air is flowing across it in the opposite direction. But right near the ball, there is a thin layer of air dragged around. As oncoming streams of air pass the ball, the side moving in the same direction as the spinning ball is accelerated, follows the curve of the ball, and is deflected off to the right. The side that is moving against the spinning ball meets opposing air and can't continue around the ball. It slows down and goes straight. We end up getting a net flow of air to the right, and the ball must move left.
Wait, that's Newton's third law.
Yes, thank you, Kyle. Just like a rocket, if you push a gas one direction, namely downwards out of the rocket, then the rocket has to go up.
So what you're saying is my shot is like a rocket.
Yes. Thank you, Kyle. Like the rocket, as the air moves in one direction, the ball has to go the other direction. Also, since the air is slowing down on the right side, you get a buildup of air, which creates a higher pressure on that side and pushes the ball to the left. The airflow is extremely important. You could not make this kick in a vacuum. It's not some weird thing the ball does to itself to curve. You need air flowing across the ball to push the ball. This is called the Magnus effect.
Of course, Professor Edwards gives the same wrong explanation as Professor Shankar, but so does Albert Einstein in this article about the Flettner rotorship. So I guess at least they are in good company.
So here's another example. If you have an atomizer, you have a perfume here, and you got a pump, and then you have a tube here. When you squeeze that pump, the instant you squeeze the pump, you're driving a lot of air here at high velocity, whereas the air here is at rest. So high velocity air has a lower pressure than low velocity air. Therefore, it'll suck the perfume and spray it right on your face.
His drawing is a bit sketchy, but it is something like this. Again, we see that he attributes the lower pressure that makes the perfume being sucked up into the airstream due to the high velocity of the air. But if we go by this principle,
And anything that's open to the atmosphere is at atmospheric pressure.
and if we calculate backwards from the opening, we will see that there is nothing in Bernoulli's equation that should indicate that the pressure at point 2 should be any less than atmospheric pressure. In fact, the air friction in the tube should make it higher. But this is how a workable atomizer could look. Just make a constriction in the tube at the point where the tube from the reservoir ties in, and the increased velocity will create a lower pressure and suck the liquid into the airstream. In fact, this should also be enough. The top of the tube from the reservoir will make a smaller cross-section in the horizontal tube, and the air needs to curve over the top of the tube, thus creating a lower pressure. But seemingly the principle appears to work as demonstrated here by Julius Sumner Miller.
Indeed, this principle of Bernoulli is why an atomizer works. You know what an atomizer is. An atomizer is a tube that resides in a vessel, and here is some liquid, and here is a tube across here, and here is a bulb, and you squeeze the bulb, air rushes across, there is a reduction in pressure, the atmosphere pushes the liquid up, and then the liquid is caught in the airstream and comes out there. I have often thought that the reason that's called an atomizer is because little atoms of the liquid come out there. Don't you like that idea, little atoms? Now, here is an atomizer, and spray would come out there. Now I'm going to show you an atomizer on large scale. Watch it. This is fantastic. Here is a tin can, and here is a tube quite like that one residing in the atomizer. And I'm going to blow a stream of air through this tube. There will be a reduction of pressure in the tin can, and now what will the atmosphere do if the can has less pressure inside? The atmosphere will collapse it because it is enormously strong. Watch it. Watch. There it is. There it is. I tell you, that's terrific.
But Miller fails to tell us that the atomizer that sucks the air out of the can looks quite different from the one in his drawing. It looks something more like this. It is very clear that the fast flowing air is drawing air and liquid along with it due to friction, and this has nothing to do with Bernoulli's principle. But instead of explaining this, he goes on to further misinform his young viewers by repeating the same wrong explanation. Professor Edwards falls victim to the same misconception when explaining why the water lock in his kitchen sink was emptied out when the washing machine drained itself for water.
Our current house in Logan, sometimes there's a sewer smell that comes up in the kitchen sink. And why is that? If there's another appliance like a dishwasher nearby, what happens is that if the washing machine or the dishwasher or whatever has a high velocity flow vent, you get a high velocity and a low pressure. I don't think you can read that, but that says high velocity, low pressure. What happens, you get a high velocity passing through here, you get this trap, and what that can do is it can empty out the trap. It can suck that fluid from the trap here, allowing the sewer gases to come up into the sink, which is disgusting. So what you do instead is you vent it to the outside so that when you've got a high velocity here, the pressure is forced to be the atmospheric pressure outside and it doesn't empty this trap.
If we assume that the drain from his house enters the sewage system at atmospheric pressure, there is no reason to assume that this would create a lower pressure which drains the water trap. But what Professor Edwards fails to note is that all drains and sewage pipes should flow at a downward angle. This is for particles and sludge not to build up and block the pipe. And when you have liquid flowing down a pipe, you will get a siphon effect. This will naturally drain the water trap if the pressure is sufficiently low. And the solution to this is to put a vent over the roof so that the pressure is equalized without draining the water trap. This is a demonstration of the so-called Bernoulli ball. This is a complete misnomer as it has very little to do with the Bernoulli principle and a lot to do with the Coanda effect. It would have made much more sense to call it the Coanda ball. It must be massively confusing to just having started to learn about fluid mechanics at school and being presented these fallacious explanations when looking this up on the internet.
The principle is that the uprushing air holds the ball up. There's some momentum transfer when the air hits the bottom of the ball and it holds it up. So that part is not so mysterious. The part that is mysterious and was to me was what happens if that ball gets off-centered? So let's say it moves to the left, and this shows the uncentered situation with the ball to the left and the stream of air going past it on the right. Well, why does that ball want to move back into that rushing air? You'd think that it wouldn't want to move back into the air and it would just fall off to the side. But what happens is that Bernoulli's principle comes into play. Over here, there's a lot of air on the right side that's rushing past the ball. And Bernoulli's principle says that if you have a high velocity, a high airspeed, then you have a low pressure. So this air on this side of the right side of the ball exerts a smaller amount of pressure on this ball than the atmospheric pressure does on the other side. So this arrow represents the atmospheric pressure pushing the ball to the right, and this represents the less than atmospheric pressure that tries to push the ball back to the left. The atmospheric pressure from the left wins and pushes the ball back into the centered configuration, where now you've got equal pressures on each side and the ball is happy.
I will let Professor Krzysztof Witkowski of University of Michigan explain what is really going on. This is to show that there are actually professors that present the correct explanation. This was a little more than a side note in his lecture about lift of an airfoil, but I included it because he very quickly summed up the problems with uncritically using Bernoulli's principle.
There's no need to use equal transit time. There's no need to think about individual molecules bouncing off the airfoil. There's no need to think about Venturi's effect or Bernoulli's equation. You shouldn't even really bring Bernoulli's equation in. The equation's fine. I have nothing against Bernoulli's equation. We use it a lot, but it gets tangled up and misused into fallacies. And actually, if you go to science museums and you see a lot of people like doing kind of these demos of, they think they're doing demos of Bernoulli's equation. You see there's things like where you have a ping pong ball and a jet of air and it's staying in place, or the sheet of paper like I mentioned before where you blow on the sheet of paper and you watch it rise up. Neither of those is a good demonstration of Bernoulli's equation. In fact, the ping pong ball and the jet of air, people say, oh, okay, the ping pong ball stays there because that jet of air is low pressure. No, that jet of air has pretty much the same pressure as the outside air because you've taken air, compressed it to higher pressure, and then blown it out of the hose. It has higher stagnation pressure, same static pressure. And actually, it's another flow turning argument, or the Coanda effect, jets staying adhered to the surface of the ping pong ball that causes the ping pong ball to stay in the middle. And that's conservation of momentum more than Bernoulli's equation. So in fact, I would say don't go into Bernoulli's equation at all. It's confusing. It's hard to demonstrate, and it has really no place in lift generation.
I will again let Diane Coven present a good explanation.
Take a ping pong ball and a source of streaming air like this vacuum blower or a hairdryer. Turn it on and place the ball in the air. It floats!
How does it work?
When the air reaches the ball, it pushes upward, balancing the downward force of gravity. The ball is balanced up and down, but why doesn't it move side to side? In fact, we can tilt the stream and the ball doesn't fall. Let's look again at the airflow. Air is deflected around the ball because, simply, the ball is in the way. Inertia tells us the air should keep going in a straight line. But the fast-moving air passes by air particles next to the ball, and viscosity or fluid friction causes the airflow to pull the stationary air along with it. That leaves a low-pressure area, which will pull the moving flow back toward the ball. This tendency for air to follow a curved surface is called the Coanda effect. The ball is also pulled toward the area of low pressure. We can see this if we blow on one side of a ball. It moves toward the side we blew on. Now, if the ball moves to one side of the airstream, the effect is increased on the opposite side, and the ball is sucked back into the middle.
This is a simple demonstration, one that you can do at home, a demonstration of Bernoulli's principle. I have one of my wife's spools for thread. I have a pin, and it's stuck through a piece of just construction paper. All there is to it. You can amaze your friends and neighbors with this one. Hollow out the spool, put the pin through the spool, and the part that's not so really amazing is if you suck up through this hole, the paper will, of course, because of the suction, I'm evacuating the hole here, and the paper is sucked up because of that, because the pressure below is atmospheric, and I've created a small vacuum in here. The more interesting one, the one that demonstrates Bernoulli's principle, is when you blow down, vertically down through this hole. So it seems unexpected that you would have thought that the air coming down through that hole would blow the piece of construction paper away from the spool. But it's not what happens. What happens instead, if this is the spool and this is the piece of paper, the airflow goes down through that center hole, hits the piece of paper, and exits to either side. Well, it exits radially in all directions, so it's coming down through here and going out in all directions. Because the velocity is high here, the pressure must be low by Bernoulli's principle. So you have a low pressure up in this region between the paper and the bottom of the spool, but you have high pressure, well, or normal pressure, atmospheric pressure, down here. So the pressure pushing up on the paper is greater than the pressure in this region, and that difference in pressure, the high minus the low, is what holds the paper in place. And that actually counteracts the effect of the air hitting the surface. The air will hit the surface and will cause an impulse, like a rocket when it's shooting out its fuel. Hitting this surface actually pushes it down. But this pressure effect, which is due to the Bernoulli principle, is the greater of the two effects and holds it in place.
It is almost amazing that I agree with Professor Edwards that this phenomenon is best explained by using Bernoulli's principle. But not so amazingly, Professor Edwards still gets his explanation very wrong.
Because the velocity is high here, the pressure must be low by Bernoulli's principle, because it's open to the atmosphere, and anything that's open to the atmosphere is at atmospheric pressure.
We will go with this principle, that a fluid exiting a system will do so at atmospheric pressure. Here is an illustration of this so-called Bernoulli disk. When blowing down through the tube, the air will exit at the rim between the two disks. At this point, the air will have a certain velocity and it will have atmospheric pressure. When moving towards the center of the disk, we will see that the air velocity will be higher, and in according to Bernoulli's principle, the pressure will therefore be lower. I have put some numbers in order to do a calculation what the resulting force would be in this example. The resulting graph for the negative pressure as a function of the distance from the center will look like this. In order to calculate the total force, one must integrate the value of the pressure over the total area of the disk. With the numbers I chose, I got a negative force of 0.071 newtons, which is about equal to the weight of 7 grams. With the gap between the discs set to 1 millimeter, I got the force of the airflow down the tube to be not more than a few % of the negative force created by Bernoulli's principle. So, Professor Edwards is not correct in saying that it is due to the velocity of the air that the discs stick together. It is due to the velocity of the air decreasing when radiating outwards.
Let's take a look at another demonstration of Bernoulli's principle, this time showing how it can apply to a gas, like air.
We are placing these containers not so far from each other, about 5 to 10 centimeters. And then Koichi is going to blow in the middle of those two containers. What do you expect that will happen? Because he blows in the middle, the containers are going to move away from each other, or if he's blowing in the middle, the containers are going to come together. Let's have a look. What you can very easily see here as the containers are drifting together. What is happening? Again, the air that Koichi is blowing through the containers has a higher velocity than the surrounding airs. Because of that, the air traveling in between the containers has a lower pressure because it's moving at a higher speed. Because of that, the pressure on the outside is pressing the two containers together.
These guys are certainly not any rocket scientists. They are astronauts. And that is good, that they are not rocket scientists, that is, because if they were, and if their general physics knowledge were as bad as their knowledge of fluid dynamics specifically, then I doubt there would even exist any astronauts. Not surprisingly, the explanation they give here is absolutely wrong, but it happens to be perhaps the most commonly used example to fallaciously explain Bernoulli's principle. Like always, Bernoulli's principle should only be used to describe the relation between velocity and pressure in a fluid along a streamline. If we do this, we see that the air starts with being compressed in Koichi's lungs. The work that he does when compressing the air will then be converted to kinetic energy. And this is because
it's open to the atmosphere. And anything that's open to the atmosphere is at atmospheric pressure.
Releasing air out of a balloon is a better analogy to blowing air out of someone's lungs, and in order to calculate the speed of which the air is released, one simply puts in the value for the pressure inside the balloon and the correct value for the density of air, which is about 1.2 kilograms per cubic meter. And that is the end of the story as far as Bernoulli is concerned. From here on, the fast-flowing stream of air will interact with the surrounding air, and this is something that does not happen along a single streamline. Surrounding air will attach itself to the fast-flowing air due to friction. Thus, the surrounding air will be removed from its original position and it must be replaced by air or whatever happens to be further out from the airstream. Naturally, this will move in towards the airstream. One can see that the boxes seems to pivot a bit so that the side of the boxes that experience the fastest airflow will move together quicker. Well, this is also easy to explain. If one imagines that one blows between two massive plates, one will see that the surrounding air will more effectively be removed where the velocity of the airstream is high. The stream of air will eventually slow down and the combined volume of the original air in the airstream and the attached surrounding air will eventually exert a positive pressure, pushing the plates apart. The boxes here are not that big, but one can clearly see this effect. This is also the explanation for the so-called Bernoulli bag.
Okay, here we go. Okay. Pretty slick, isn't it? Okay, all I did there is I actually used Bernoulli's principle, and it's kind of like cheating. Now, most kids will say you cheated.
I would also say it was cheating. He did not use Bernoulli's principle at all. The surrounding air simply got carried along with the airstream due to friction and ended up in the bag. Surprisingly, the demonstration from the International Space Station was actually provided by NASA Eclipse, E for educational. And this fallacious explanation was not the only one presented in this video. Frank Devin makes an even bigger fool of himself by showing this experiment.
They think they're doing demos of Bernoulli's equation. You see there's things like where you have a ping pong ball and a jet of air and it's staying in place, or the sheet of paper like I mentioned before where you blow on the sheet of paper and you watch it rise up. Neither of those is a good demonstration of Bernoulli's equation.
This is a principle, of course, that I have used a lot in my previous career because I used to be a pilot. And this is how airplanes fly. If you look to the wing of an airplane, you see that it's curved, always a little bit towards the bottom. The side on the top side is longer and is more curved than the bottom side. This means that the air traveling on the top of the wing will travel faster than the air underneath the wing, creating a lower pressure and lifting the wing up. This is what we call lift. And because of this lift, we can travel and we can fly all around the world.
And this is what NASA says about that theory. NASA points out that pushing wrong theories like this is causing unnecessary confusion among students. It is funny then that NASA writes on the site for NASA Eclipse, Professional development opportunities are delivered to demonstrate best practices using newly developed resources to address student misconceptions in science as identified by national assessment sources. This is not impressive by NASA. I really find it difficult to express what I think about this. It's
disgusting.
Well, one could say that NASA did address student misconceptions in science, but not in a good way. There are actually some more examples I could have addressed, but I think I will leave it with this. In my next videos, I will show how misconceptions in fluid dynamics manifest themselves in the making of the most bizarre contraptions. Einstein wasted quite a bit of resources on his doomed-to-fail wing profile, and in the following century there is no shortage of equally stupid attempts to circumvent the laws of nature in order to draw funding and attention from projects that actually could have had a positive impact. I think I will start with this one. I think it is absolutely unbelievable that anyone can look at this concept for more than 10 seconds without concluding that it is just one big pile of rubbish, and much less how it's possible to waste public money on it. Until then, have a good time and stay away from misconceptions.